Right. We begin today with an exercise that is probably not important, but it's a chance for me to show off, actually putting myself on the edge to see if I can do this. I want to develop the dynamics of uniform circular motion. So I have an object traveling along the circle at constant speed, and at any moment it's going to be r away from the center, the radius, and it's going to be at some angle theta, and that theta is going to change with time, but at a constant rate as it goes around. So at this time that it's here at this angle theta, its position is going to be given by r cos theta over and r sine theta up. But its velocity, of course, is tangent to the curve, and so the velocity then will be made up of the x component, which will be in the negative I direction, and the y component. But these two components are legs of a right triangle, and I can argue that this angle theta here is the same as an angle theta that would be right there to the horizontal, complementary to that angle, which is also complementary to this angle. So ultimately I can argue that this angle here is also theta. And thus it follows that this is the magnitude of the velocity times the sine of theta, and this one here is the magnitude of the velocity times the cosine of theta. And thus, and if I come back here, I can see that the cosine of theta is going to be equal to x over r, and the sine of theta is going to be y over r. So ultimately, this expression for the velocity that we had here can be written this way. There is v sine theta in the I direction and v cos theta in the j direction. Now I will take this equation and I'm going to differentiate with respect to time, realizing that the velocity has constant magnitude. We are going at the same speed. The direction keeps changing, and that's important that the direction keeps changing. It is vital to this solution. So this quantity here is not a constant, but this here would be the magnitude of the velocity, and it is constant. The y, of course, is changing as a function of time. As you go around, the y values keep changing with time, and so do the x values. R, however, is a constant, and of course these unit vectors are constants. So when I take the derivative of the velocity with respect to time, which is equal to acceleration, you can't see it. It's going, these two terms, the v and the r, are constant, so it's just dy dt. And here in this term of the polynomial, it's just going to be the dx dt is the only thing that changes as a function of time. But what is dy dt? Why, that is an expression for velocity. That's the y velocity, which was equal to v cos theta. And dx dt is the x velocity, which was equal to v sine theta, or negative v sine theta. So I put those values in, and now we have v times v. So you've got that a is equal to negative v squared over r. It's the cosine of theta in the I direction, and negative v squared over r times the sine of theta in the j direction, that you can see that we have that the magnitude of A is going to be v squared over r, and that the direction of A is going to be given by the inverse tangent of the y term, this times the sine of theta, negative that times the sine of theta, divided by the x term, which is negative this times the cosine of theta, which comes out to this value. That is, you're taking the inverse tangent of the tangent. That just gets you a theta, except we need to pay attention to those negatives. It's going to be in the third quadrant. So when the position vector was going out here in the first quadrant, the acceleration vector will be going in the third quadrant. That's exactly the result we've always known, that the acceleration is centripetal. It's going opposite to the direction of the radial direction. And thus we have the result that when you travel in a uniform circular motion, your acceleration is equal to v squared over r, and its direction is towards the center of the circle. I'm just very pleased that the derivative will do all of that for us. And if we use it correctly, get that result. But we move on to that which is of greater consequence, and that is doing relative motion problems, dealing with inertial frames of reference. And many of you were exposed to this last year and probably discounted it, said, oh, I can do these problems without learning this new technique, and so you did. And I promised you that the problems would get hard and you would need the technique, and maybe you never did last year. But I'm telling you that it will make your life much easier if you will learn this technique. So here I have a reference frame B dotted, and reference frame B is moving relative to reference frame A. Here's the velocity of B relative to A. This notation, which is read as the velocity of B relative to A, very, very good notation to learn. Notice that I have an object at some position P. P means different things in reference frame A and reference frame B. Here is the location of P relative to reference frame B, and here is the location of P relative to reference frame A. But note how, if I use this subscript notation with I want the location of P relative to A, and I know the location of P relative to B, then I would add on the location of B relative to A. That if you add this vector onto this vector, you do get the position of P relative to A. That the way this works with the subscripts is you write one of the vector quantities here, and you put those subscripts, and then here you take that first subscript and it goes in the first position, and the second subscript goes in the last position. And in between, this second subscript of the first term and the first subscript of the second term need to match one another. And then you have a working equation. It really is wonderful, and it works great. And if we then take the derivative of both sides of this, then with respect to time, then you do get the fact that the velocity of P, this point, its motion relative to reference frame A, is equal to the sum of its motion relative to reference frame B and B's motion relative to A. And the same with acceleration, except note that when I take the derivative of v sub BA relative to time, it was moving at a constant velocity. It is not a function of time, and so this yields you a 0. And so we have that the acceleration of P relative to reference frame A is the same as the acceleration of P relative to reference frame B. If we were to throw in the mass of this object here, we could talk about forces, and the forces would be the same in both reference frames. That's what makes it inertial. It is very powerful that the changing the reference frames, as long as they're inertial reference frames, does not change the forces or the accelerations. Now, if this had been accelerating, then you would have a non-zero term being added onto this, and the accelerations would be different in the two reference frames, and so the forces would be different in the two reference frames. And you have the situation where if you're in an elevator that's in free fall, you are weightless. You have no force on you. Whereas outside of that elevator, in the reference frame of the Earth, yes, you do have a force on you, and that's what's making you fall. That falling elevator causes you to invent pseudo forces which are holding you up and making you weightless. Or when you go around a curve, that is, again, if you're inside of a car going around a curve, that's an accelerating frame of reference, not an inertial frame. You do have a term for that acceleration, and it causes the forces inside of the car to be different than the forces outside of the car. Inside of the car, you say there is outside of the car, you would say there's centripetal force accelerating you towards the center. Inside of the car, you feel as if there is something pushing things to the outside of the car. You invent a centrifugal force, a pseudo force, because you are operating in an accelerating frame of reference. We can extend these ideas of frames of reference to space, and instead of x's, we'll use an r for the spatial position vector, and the same rules happen, the same technique, that adding the velocity of the object relative to reference frame B onto the velocity of reference frame B relative to reference frame A does get you the velocity of P relative to reference frame A, exactly as you would hope, and very nice extension into 3 dimensions. Finally, application of this relative motion formula to problems, and again and again and again, I cannot emphasize how good it would be if you would come along for the ride and adopt this new approach to doing relative motion problems. First step, recognize it as a relative motion problem. The word bearing gives it away. Then pull the information with these subscripts because you recognized it as a relative motion problem. The plane has a bearing. That bearing is a code word that means motion relative to the fluid that you are moving through. So if it's an airplane, it's relative to the air. So there is the velocity of the plane relative to the air. I don't know how fast, but it's going at 40 west of south. The wind is blowing at 40. Again, they didn't tell me the direction of the wind, but they did tell me how fast, the magnitude. So the velocity of air relative to Earth. I would not want to call this wind because that would lose the fact that that's a common variable. So you have to think ahead and make the system work for you. This would be the air relative to the Earth is 40. I don't know what direction. And finally, the question. Oh, no, wait a minute. The plane is observed from the Earth to move at 15 at 20 west of north. So that's the plane from the Earth, the plane relative to the Earth. So the velocity of the plane relative to the Earth is 15 at 20 north of west. This is not a turnkey operation. It takes some effort to get these subscripts right and figure out what those subscripts should be. But once you have done that, here they want to know what is the direction of the wind, which I've called air here. But even if they had wanted to know something like the magnitude of the plane relative to the air, I would take the vector whose direction I do not know and put it to the left isolated equals to the sum of the other two vectors. But when I add up those two vectors, I'm very careful to make the first letter correspond to the first letter there, and the last subscript correspond to the second letter there, and that the letters in between match up. And then we have this what I call the relative motion equation, and then I can go ahead and do what the relative motion equation says to do. It says take the velocity of A relative to P. Here I've got P relative to A. So A relative to P is going to be going south. No, it's going to be going east of north, exactly the opposite direction to P to A. Because the subscripts got inverted, this is going to be 40 degrees east of north. So I'll draw that vector. I don't know how long to make that vector, but I do know what direction it goes. I'm going to go ahead and mark the angle here because I'm going to have other vectors up there, and I don't want to put the 40 there in the way. But 50 north of east is the same as 40 east of north. Again, opposite direction because the letters got in the opposite direction. And then this says to add on the plane to the earth, which is 15 at 20 north of west. And so I will draw a vector whose magnitude, this is the length, is supposed to represent 15, and it's supposed to be going at 20, 20 north of west. And what this says is if you add those two vectors, this one has magnitude 15, I don't know the magnitude of this one. If you add those two vectors, you get the air relative to the earth. And so the sum of those two vectors would be a vector which goes from here to here, which I messed up. So we'll fix it. Oops, not you. Boom, boom. Turn. About there. Make you a little shorter. Oh yeah, we're good. Okay, so there is the sum of those two vectors, and that would be the velocity of the air relative to the earth, which I happen to know has magnitude 40. Now, there you have made the triangle, and what I want to know is this angle right here to get the direction it's going. If this angle is 50, then this angle up here is 50, and then I can use the law of sines that the sine of this angle, 70, is to the side opposite 40, as the sine of this angle that I'd like to find is to the side opposite 70. Comes out that that angle is 20.6 degrees. But then I need to add that on to 50 because we always measure directions from a cardinal direction. And so the 20.6 added on to 50 gives me that it's going to be going at 71 north of east. That's the way to do that problem.